Hey everybody, Dr. A here, and in this video we're going to be discussing and exploring an accompanying example of how to compute the first area moment, which we often call capital Q, that's used for beam shear stress and shear flow calculations in mechanics of materials. Okay, so the reason why I want to have a video that only discusses capital Q is because this tends to be a source of confusion for a lot of students learning this for the first time. A lot of people make mistakes and get confused by this capital Q value. Okay, so let's go ahead and start discussing it. So again, capital Q is often called the first area moment because basically the way you calculate it is you take an area and you rotate it through a perpendicular distance about a particular axis. That's how you do it in general, okay? Now, why is it important and when do we use it? Well, we often use capital Q when we are computing beam shear stress and shear flow, which we typically learn in a mechanics of materials course or possibly a structural analysis type of course. So if we recall from our knowledge of mechanics of materials, we use tau as the designation for beam shear stress. And in beam shear, tau is equal to VQ over IT, okay? V is the internal shear force at the section we're interested in. Q is the first area moment that this video is really dedicated to. I is the moment of inertia about the bending axis. And T is the thickness within the cross section where you want to compute tau, okay? Now, we also see capital Q when we're performing shear flow calculations from mechanics of materials. We typically use little q to designate shear flow, and that's computed as VQ over I, very similar to VQ over IT, just without the T in the denominator. So again, in this video, I'm really not concerned with beam shear stress and shear flow. I really just want us to focus on capital Q, okay? So let's go ahead and take some notes and then do a numerical example. So Q, this capital Q, the first area moment, for our purposes is going to be computed as Y bar prime times A prime, okay? Now, what does this mean? Well, A prime is going to be the area that is at the top or of the top, and I'm going to put in parentheses. This is going to sound confusing at first, but that's okay. We're going to explain it. Or bottom portion of the cross section that is above, and again, I'm going to say something a little confusing in different colors, or below the section plane where tau is being computed, okay? Tau is computed, this is again if we're dealing with beam shear stress, tau is computed on a plane of thickness T within the cross section. Okay, so here's what I want you to do. Maybe pause the video, write this down, and think about what we mean by A prime, okay? Again, area of the top, and then in a different color, I said or bottom portion of the cross section that is above, and then in a different color or below the section plane where tau is being computed. And when you're computing tau from mechanics of materials, it's computed on a plane that has a thickness of little t within the cross section. So that's A prime, okay? What about this Y prime bar? Y prime bar is going to be the perpendicular distance from the centroid of A prime to the overall cross section's centroid. Okay, now here's what I'm going to do. I'm going to draw two different figures here that are illustrating this explanation here, the top or the bottom, above or below phrasing, okay? So let's draw one figure here, okay? This is just a blob of a cross section, okay? Now, anytime you see in a textbook or your professor draw a general blob like this just means it could be any shape. This could represent a rectangle, it could represent a T shape, an I shape, it could represent any shape. So we typically do this as an arbitrary body, or sometimes it just looks like a blob, okay? So let's say that I want to calculate the shear stress on this plane right here that has a thickness of T, okay? So this thickness right here, where I want to calculate the shear stress, has a thickness of T, okay? And I can even go ahead and draw some little vectors here to indicate this is where I want to calculate my beam shear stress tau. Now let's look at this explanation. It says A prime, I'm going to change colors again now. A prime is the area of the top. I'm gonna forget about my green or statements here for now. Let's just read it without the or statements. Area of the top portion of the cross section. So that means this portion of the cross section that is above the section plane where tau is being computed. So if I want tau to be computed on this section plane, this little area that I just hatched in blue, that is my A prime, okay? So this right here is my A prime, all right? Now, let's say that my centroid location, my neutral axis of the entire shape, say NA of cross section, is right here, and here's my centroid of the entire cross section. So y prime bar is going to be the perpendicular distance from the centroid of A prime, which is going to be about right here, to the overall cross-section centroid. So this is going to be my y prime bar, okay? Now, that is the first phrasing. Let's do the same thing, but let's now read through the or statement. So how about this? I'm going to redraw what's supposed to be the same cross-section. It doesn't really look like the same shape. So let's say that that's the same cross-section, and let's say everything's the same. Here is that thickness T that I'm interested in. Here is the shear stress tau that I'm interested in, okay? Here is my overall neutral axis of the entire cross section, okay? Now let's read the description of A prime, but this time using the or statements in green. A prime is the area of the bottom portion of the cross section that is below the section plane where tau is being computed. So where is A prime going to be based on my green or statements? Well, that would be this entire area right here that looks quite a bit bigger. That would be A prime. Now, let's say that the centroid of this A prime is, say, right about here, okay? So y prime bar is the perpendicular distance from the centroid of A prime to the overall cross-section centroid. So that would be this distance right here. y prime bar. Now, this again is still the same cross section. So you might be wondering, how in the world could both of these be true, right? I mean, it says that Q is equal to y prime bar times a prime. How could I use either of these? Well, the truth is I can look at either one of these diagrams and compute Q, and I would get the same thing. Why is that? Well, the reason why is because even though A prime is different between these two different depictions, so is y prime bar, okay? So in this left diagram here, A prime is some value and y prime bar is some value, and you take their product and you get Q. Well, then if you look at this right diagram, A prime is a different value compared to the left diagram, and y prime bar is also a different value compared to the left diagram, okay? So the way I explain it when I teach my students this concept in class is I say, think of how many ways there are to calculate the number 12 by multiplication. You can say 6 times 2 is 12. You can say 3 times 4 is 12. You can say 12 times 1 is 12. Those are 3 distinct ways we calculated a value of 12 by multiplication, okay? In each case, the answer was 12, right? 6 times 2, 3 times 4, 12 times 1, all equal 12, okay? So it's the same idea here, okay? You are interested in the product of A prime times y prime bar. Now, if you look at this kind of diagram, A prime times y prime bar will give you Q, and if you look at this other setup over here, A prime times y prime bar will give you the same Q value as long as you are looking at the same section plane of T and your cross section is the exact same, okay? So let's go ahead and do a numerical example with an actual shape that can help us see this a little bit more clearly, okay? So I want us to compute Q by part A, taking the flange area as A prime, and part B taking the web area as A prime. And then in both of these cases, tau would be computed at the flange web interface. Okay, so let's go ahead and do this. Our cross-section area, this is all given information, by the way. Our cross-section is going to look like this. This is 2 inches, this is 10 inches, and then three inches, 2 inches, and 3 inches, okay? And this right here is the flange web interface, okay? So this right here is the flange, and this is the web. So if we're interested in the flange web interface, then right here is that interface we're interested in, and the thickness would be 2 inches. That's the thickness, little t, we would be interested in. But again, we're not really interested in that. We're just interested in Q, okay? So let's go ahead and say solution. And of course, Q is equal to A prime y prime bar, okay? And so part A says take the flange area as A prime. So again, we need the overall centroid of the entire shape. So we're going to say compute regular y bar for the entire shape. Okay, so I'm going to put a little green datum here. So again, we first need y bar for the entire shape because we need the centroid of the whole shape for eventually our use in y prime bar, okay? So we're going to say y bar equals a1 y1 plus a2 y2 all over a1 plus a2. So a1 is, let's see, 8 times 2 is 16 inches squared. Y1 is 11 inches plus A2 is 20 inches squared. Y2 is 5 inches. And then the total area is 36 inches squared. So Y bar measured from the bottom is, I'm punching this in my TI 36X Pro calculator. So I get 7.667 inches measured from the bottom right there, okay? I did that pretty quickly because this step, this centroid step, is just a static step. So that's, hopefully you remember that from your knowledge of statics. So now let's look at part A. So we're going to say A prime is the area of the flange, okay? So it's this area right here. So that's going to be 8 times 2 is 16 inches squared, okay? So if I redraw this, I'm going to try to redraw this T shape. There's my A prime, and that's the regular Y bar, 7.667 inches. The Y prime bar is going to be the distance from the centroid of A prime to the overall centroid of the shape, okay? So my Y prime bar is going to be what? Well, I can say 12 inches minus 7.667 inches minus 1 inch. So my Y prime bar is 3.333 inches, and Q is computed as A prime Y prime bar, and I get 53.3 inches cubed. Okay, now let's look at part B. Part B was take A prime is the area of the web. So looking back in our original figure, the area of the web is 10 inches by 2 inches. So that's 20 inches squared. And again, I can redraw this. This may take a little extra time because we're redrawing things over and over again, but that's the best way to learn, is by redrawing and resketching things as needed, okay? So here is Y prime bar. I'm sorry, not Y prime bar, A prime for the second part, and my regular Y bar is still the same. That's the overall centroid. Okay. Now I need the centroid of A prime, okay? A prime centroid is half of this 10 inches, right? So let me sketch this just a little bit better. So my Y prime bar is this distance, Y prime bar, and again, the overall centroid here, the centroid of A prime is just my 5 inches here. So Y prime bar is 7.667 minus 5 inches, so 2.667 inches. And then Q in this case is, sure enough, 53.3 inches cubed. Now, again, you want to watch out for round off error. That could introduce a little bit of error there. But again, you can see that in both cases, we get the same Q value. So I know I went kind of quick through some of these calculations, especially this green overall centroid calculation. If you're a little rusty on calculating just a regular centroid of an entire shape, take a look at my statics playlist, because I've got a couple videos that can refresh your memory on that. But in summary, this video is just to illustrate and exercise how to calculate that first area moment Q that we use in our mechanics of materials beam shear stress calculations. So hopefully you found this helpful. Please hit like and subscribe and be on the lookout for other content similar to this. Thanks for watching.